Welcome back to Advanced Algorithms. Welcome to the third session in our course. Last time we talked about pseudo-polynomial algorithms that are algorithms which are in general not in polytime, but if one of the if this parameter of the input, the maximum integer that occurs there, is bounded by a polynomial, then the algorithm was a polytime algorithm. So we've subdivided the class of NP-hard problems or NP-complete problems into those that have such a pseudo-polynomial algorithm, which is then, at least for certain instances, fast enough in practice, and algorithms or problems that are strongly NP-complete, which meant that even if they only consist of small numbers, they're still NP-hard. Today we will talk about a similar idea that takes this to a higher level and makes it, applies the same idea in a more flexible way. We'll talk about fixed parameter tractability, and later in the course, not today, we'll talk about how to make algorithms that are exponential in the input size, if you just look at it as one thing, still efficient in certain circumstances. Okay, let's make it a bit more concrete by considering an example. The idea that we want to follow in this whole chapter is that we refine the complexity analysis in 2 dimensions, whereas before we only had 1. So the old one is just the size of the input, by which I mean the size of the input in a sensible encoding as a formal language as we had it. And well, this is usually what we will call n. And the second thing is a parameter k, we will usually use to denote it. And this can be all sorts of different things, and I'll give you an example in a second. The new thing is that we will measure running time in terms of both of these. So we refine complexity analysis in 2 dimensions and investigate what is the influence of various parameters. So the idea is that we will try to make this flexible so that we can choose different parameters. Depending on the problem, one might work out, others might not. The hope from a practical point of view is that we find a parameter for which the problem can be solved efficiently, well, not always, but for small values of the parameter. And this does not necessarily mean that also the input size itself is small, so it's a refinement. And the ideal case that we're hoping for is that this parameter is actually also small in practice. So here I simply wrote k should be small. We will make this much more precise what I mean by this in a second. But let me first give an example for some parameters for a well-known problem. So you might know what Drosophila is. It's a fruit fly, and it's maybe one of the most studied and best understood creatures that we have in nature, because biologists, whenever they try out a new field of study and would like to try new methods that they develop, then they first try to explain it on Drosophila. And we have a similar thing in complexity theory. Let's look at our Drosophila. The Drosophila of complexity theory is C and Fz. Ordinary satisfiability was the mother of all NP-complete problems, as we've seen last time. Now we restrict it a bit. We only allow formulas in conjunctive normal form, because that gives us a few more parameters that we can choose. One possibility for a parameter is the size of a clause. So we can restrict each of the clauses in the formula to have at most k literals. We might also say it's exactly k literals. That doesn't make a difference, because we can always fill up empty literals by copying existing literals. That doesn't change the value of the formula. We know that there's a sharp threshold in terms of complexity. For k equals 2, we get the problem 2 sat, which also is well studied, and that's a polytime problem. We didn't discuss algorithms for it, but it's fairly simple. Whereas for 3, we had the list of NP-complete problems, and there 3 sat was one of them. So for k equals 3, we already have an NP-complete problem. So in a sense, this is a bad parameter in the theory that we're now looking at, because even for small values of k, we already have an NP-complete problem, and of course it stays such if you further increase k. So if you find an algorithm that depends on the k and running time, that doesn't really help much, because k will usually be small and the problem is still hard. So let's look at a different choice for the parameter. What else can we take? Well, we could take the number of variables in the formula. That's a natural parameter as well. And indeed, we can then solve the formula just by the brute force method with roughly 2 to the k times n steps, because 2 to the k is the number of different assignments, and if we try out each, then we need linear time in the formula in terms of the number of steps that we evaluate the formula. If we want to be very precise and compute the exact running time in a logarithmic model and so on, there might be a few more factors, but a rough estimate of running times, if we only look at poly time versus exponential time, it's sufficient to state it like this. This is already by the brute force method. And in fact, for 3 sat, people have found an algorithm that replaces this 2 to the k by some 1.49 to the k. And again, some factors, some polynomial factors in n in the length of the formula, which is quite a sensible reduction if k is indeed small. And this is a better parameter than the one we had before, because the formula is, the problem is not hard if k is very small. We see that then if k is a constant, the problem is pretty easy to solve. But it's also not a perfect parameter in the sense of our theory, because in many applications the number of variables in a formula will grow a lot if you make the formulas bigger. So it might not help that this algorithm has a low dependency on n, if k is still large, it's still not an efficient algorithm. And of course it's not. It's just this stupid brute force method, and people are not using that for solving SAT. Now we have still other choices. We can also pick the number of clauses in the formula. Say, if we have m such clauses, there's a 1.24 to the m algorithm for solving the formula, for solving the SAT problem. But then again, this is certainly a parameter that grows if we make the formula larger. So it's still not what we're aiming for. Similarly, we can use the length of the formula by counting the number of literals. Here again, we cannot hope for an L that's very small, but maybe surprisingly people have succeeded in bringing down this base of the exponentiation even further for this parameter. And then you can do also all sorts of wild things. Maybe you want to take as parameter the weight of a formula, which would be the number of 1 entries in satisfying assignment. So this is an interesting parameter, because if you change the formula only a bit, then this weight might change a lot. But it's a thinkable parameter, and maybe it helps to use this one to get a good algorithm. In a more generic sense, you could use any kind of structural properties of the formula. For example, each formula represents a graph in the sense that there's nodes for the literals, and you can add edges for the interplay between the literals if they're in the same clause, for example. And you can use any kind of measures on this graph as a parameter for the formula. It's a bit unclear whether this helps in solving the SAT problem or not, but it's a thinkable parameter. Here we've only talked about the ordinary decision version of SAT. You can do similar things for the max SAT problem. And there you have an additional parameter that you can take. So let me add for max C and F SAT. An additional parameter might be the threshold that we are interested in. So the decision version of this optimization problem asked for, is there an assignment that satisfies at least k clauses? And you can make this k, the threshold that you're given as input, you can make this your parameter. As we'll see, this will often help. But in general, it's a huge field where you can pick your parameter freely. And this is what makes the theory interesting. Gives you a lot of freedom and a lot of choices for how you might best tackle your problem, and sometimes surprising parameters give interesting results. So let's formalize a bit the ideas that I've just informally discussed now. And we go back to words and algorithms on strings as usual. So first of all, a parameterization is nothing else than a mapping from the set of all words to the natural numbers. We only require that this should be a polytime computable function, which will, the reason for that is to make certain definitions then similar, but This is not really a restriction, as we'll see in most cases. If you think back, certainly for a sensible encoding of a formula, we can devise a polytime algorithm that counts the number of different variables that occur in this formula. Or it could count the number of clauses in the formula. These are all parameterizations that are easily polytime computable. Now a parameterized problem, a decision problem as usual, it's a pair of a language L and some parameterization kappa for the same alphabet and nothing else. So this is a very wide definition in a sense, and it makes sense here, or makes definitions later a bit convenient to separate these two properly. But as we'll see, it's sometimes for some problems a more convenient way to define a parameterized problem would be to define a language of pairs, so that for each x in the input, there's the parameter as second parameter. The parameter for the instance x is given as the second entry of this pair. So what we require in this case is that whenever we have the same instance in the language for certain k, then these should be the same parameter, and it's nothing else than saying that this mapping is a well-defined function. Whenever we start with such a language of pairs, a set of pairs, we call this the canonical parameterization that's at work, which is just defined by the projection to the second component of this pair. Let's look at a few examples of parameterized problems before we go on. We will usually not give sigma explicitly, but as we did for ordinary decision problems, we will just state what's given in the problem and what's the question that the decision problem asks us to answer. Now we have a new thing, which is also the parameter has to be specified. Then here's a naming convention for problems. If SAT, for example, is a decision problem, we add this prefix p to denote the parameterized problem. It should be clear that this is formally a different thing. The parameterized problem is a pair of a language and a parameterization kappa, whereas the decision problem was just the language. So here's two examples that you've already seen in a sense. So psat should, if I don't write anything else, then it's parameterized by the number of variables. And we've already discussed this a bit. Then there's different choices for the parameter, but this is one version. And for the clique problem, we can parameterize by the k that's given. So recall the clique problem is we're given a graph and some number k, and we ask for, is there a subset of k nodes so that any two are connected by an edge, and then k is just the parameter that we ask for. Now let's start below here. The naming convention for the general case is that we just add some specifier for the parameter here in case there are several. So for example, our CNF set that we've discussed before, the Drosophila, can also be parameterized with respect to the number of clauses. Then we would write it like this. Now for optimization problems, like the ones given here, there's a canonical parameter, which is the threshold that we're given. I've mentioned it before with the example of maxsat. Now formally, if we're given such an optimization problem, we call the definition as a 7-tuple that we've seen last time. Then we write pu for the following problem, namely the canonically parameterized decision problem, which is given just by the threshold language. So you might recall that the threshold language again was the set of all pairs x and k, for which the instance x has a solution that's weakly better than k. So this is, let's it's maybe not precise enough that half solutions that are weakly better than k. For example, the p-clique problem would then be the one that we've just given. The p-vertex cover problem would be the vertex cover problem parametrized by the k that we're given, and so on and so forth. So this is often a good parameter to consider. Therefore, we say we omit the specifier if we mean the canonically parametrized version. Before I formally define what I mean by fixed parameter tractability and FPT algorithms, the topic of this chapter, let's first consider a few examples of how running times in terms of this parameter k and the input size look like. And to keep things simple, in this introductory section, let's only consider simple brute force methods. And just compare what the running times are. So the intention of this part is not to give you the fanciest algorithms for the problem that I present in a second, but it's discussing the types of functions that occur as running time bounds. Okay. So the first problem would be our good old friend SAT, the Drosophila. We have k variables. I should write psat. Recall that psat, we just defined it as parameterized by the number of variables. And say n is the length of the formula measured maybe in the number of occurring symbols or literals. We'll only use it in terms, in big O terms, so it wouldn't make a big difference. As I mentioned before, we have 2 to the k candidate solutions. So the search space for the possible certificates of a yes instance of a satisfiable formula is 2 to the k. And each can be checked in, say, linear time. Here I'm a bit, as before, I'm a bit sloppy with the exact cost model maybe. But it's certainly a polynomial. And if you think about the class NP as how we defined it in terms of verifiers, this is always a polynomial if the problem is in NP. If this is the set of all certificates that are possible, then this must be a polynomial. So what we have in this instance is 2 to the k times n. The next example is p-vertex cover. Let's do p-clique first. For clique, we use the canonical parametrization, so k is just the threshold. Is there a set of at least k nodes, so that, and n is the number of vertices in the graph, or nodes, and m is the number of edges. Now what's the possible certificates for clique? Well, that's all the k element subsets of the nodes, and there are so many. So this is the number of candidates that we have. To find if it's a clique, we just have to check the k-squared pairs in one of the sets for whether there's an edge. So the time to check one of these candidates is roughly k-squared. So that gives us an O of n to the k squared. Now here, if if this is not so familiar to you. The binomial coefficients can be written as n to the k falling divided k factorial, where this is just n times n minus 1 and so on, k terms. So you always make it one smaller. So this is always at most n to the k, which is sufficient for our upper bound here. So this is a different running time, because now we have n to the k and not a fixed number. So we would probably like this algorithm much better, right? But we can do much worse. Let's first consider vertex cover, which is very similar. So we have the same parameters, the same size thresholds, size parameters. And again, so recall vertex cover was the problem that we have to pick a subset of the nodes so that each edge is covered with one of its endpoints. And if we ask for, is there a vertex cover that has at most k nodes, then all we have to do is check and choose k candidates. And to check one, so maybe right like this. To check one of these candidates takes linear in a number of edges, say. If you combine these, you again have n to the k and now times m, which is a bit more than this, but usually not too much. As the last example, let's consider the parameterized version of graph colorability, graph coloring. There k was also a threshold. You can formulate graph coloring as an optimization problem. Now here it's a threshold, and that's just the number of colors that you may use for a graph with n nodes and m edges. Now you have to assign every of the nodes, each of the nodes, one of these k colors, so that for each edge in the graph, its endpoints have a different color. That was the definition of graph coloring. Now the number of candidates is way larger. You have k different choices for each, and you have n nodes. Now by symmetry, a few can go, so you might replace this by k minus 1 without much trouble. But in general, so this is the brute force method. We'll just check them all. And it's not so clear how you can improve on that much. Now for the check, if a given coloring is feasible, you have to look at all edges and check the color of the endpoints. So it's again essentially linear in the number of edges. And this gives you the overall running time of k to the n times m. Visually very similar, but of course mathematically a much more troublesome result. Now all of these are parameterized running times where there's a dependence on the parameter and the dependence on the input size. N and m essentially are the input size. Here you could make it one parameter. But the question is where to draw the line. Which algorithms are we considering efficient and which ones are already inefficient? We had a similar discussion with P versus NP. There we defined in the end that as long as the running time is bounded by a polynomial, we are calling it efficient and the problem tractable, which in a sense was a lie even for that definition already. I mean, just because it's bounded by a polynomial doesn't mean it's really usable in practice. But except for a few hideous instances and examples of problems, you usually have a small exponent and then it's usable in practice. even though we don't have guarantees. Here again, we should make such a decision, but it should be a sensible one. So let's just try what values of k we can use. If down here we say k is a constant, we can even give a specific constant, then the problem is already NP complete. So graph colorability, checking whether it's colorable with 3 colors is already NP complete. And if you insert that here, 3 to the n, that's still a very large number. So this is certainly something we would not like to call efficient. For these two, vertex cover and clique, we can at least allow some bound at k. It doesn't have to be smaller than 3, as long as it's bounded by some constant, even if we don't know it. These are polytime functions. That's a polynomial in n. If we have anything larger than constant, then it's no longer polynomial. Here we can go a bit larger. We can even allow logarithmic in n. Then this would be still a polynomial. But we can also not go much larger than that. If we, for example, picked log n to some c, to an exponent c, say 2, then already for k equals log n squared, we'd have 2 to the log n squared, which is n to the log n, if we take log to the base 2. And this is already no longer polynomial. In fact, this class, if you allow an arbitrary c up here, if you have any c greater 1, then this class is called, sorry, this was still to the c. This is called quasi-polynomial. And even though it's not quite polynomial, it's not so bad, but it's, yeah, not, in terms of p versus np, it's not polytime. But still we can allow logarithmic parameters. And as we'll see, we will basically draw the line between these two. So a parameter dependence like this will still be okay, whereas this is already too much if we can't even pick a constant parameter. So the definition looks like this. We define an algorithm is efficient with respect to a parameter, so fixed parameter tractable, if this algorithm A has a running time of this form. There's a polynomial in the input length times a function of the parameter. K is just the parameter of the given instance. And this function f may be an arbitrary computable function. It could grow humongous even for small k. We allow that and still call the algorithm FPT, fixed parameter tractable. The reasoning behind this is that as long as k is really, really small, it won't hurt too much, even though that function might grow very, very quickly. So we defined an algorithm as FPT runtime, if you like. Now a problem, a parameterized problem, recall it was a language and a parameterization kappa, is tractable, FPT tractable, fixed parameter tractable, or FPT, if there's such an algorithm. And the class of all such problems is denoted by FPT. Now intuitively, this is the equivalent of our class P that we had before, and always treated as the simple problems. And of course, this is a bit debatable. If f is really a large function, then these will not be solvable in practice. But the same is true for P. If there was an algorithm with a runtime n to the 100, that would also hardly be practical. Now let's consider an example that we've essentially already seen, but let's write it down as a theorem just to exercise the definition once more. We consider the SAT problem parameterized by the variables. I wrote it as psat before, and we will continue to do it. I just explicitly mentioned variables here to be specific and to remind you what I mean by it. So we claim that this is an FPT. Well, we have to find an FPT algorithm, that is. And essentially it's just the observation that the brute force method does the trick. Because its running time was given like this, so there we already have our form. A function that only depends on k times a polynomial in n. That's an FPT algorithm, which means that the problem is in FPT. Now the only catch at this point is the number of variables is not usually small, so this result is not very helpful. And in fact, there's a general theorem that tells us a bit about the corner cases of this FPT class and guides us towards sensible parameter choices. So the point that, let me stress this maybe once more. One thing is that the FPT class allows very large functions, which makes it sometimes an impractical algorithm, even though it's an FPT algorithm. But here 2 to the k is not as bad. I mean, for sensible k, this would still be a reasonable number. If k is 300, no more, but for small, say 10 or so, this would still work fine. But there's another problem with the FPT class in the definition, and that is if the parameter doesn't do you the favor to be small, then you're making hardly any statement about the quality of the algorithm. And this is what the following theorem is supposed to show you. Let's start here. We have a language L that's just any decidable language. It could be extremely complex from any of the hideous classes that are out there. And this is still FPT with respect to any parameterization that fulfills this property, that has this property. Namely, the parameter of an instance is greater than a function of the size of the instance. And for this function g, we only need that it's weakly increasing, unbounded, and computable. So computable is fine. I should comment on weakly increasing. I prefer this terminology to the more standard non-decreasing, because non-decreasing is like not saying what you don't mean. I prefer to give it in the positive direction. So increasing would be just whenever you make the argument of the function larger, the function has to go up strictly. Weakly increasing means we have less or equal here. So we only need this for integers, so this is sufficient. And unbounded, a function is unbounded if it attains any value for large enough parameters. So let's quickly give a proof before we discuss the consequences further. We assume that L is decidable. That means we have some algorithm that decides this language, and that means there's a function bounding the running time of this algorithm. So the question is X in L is decidable in time at most t of x steps. Now this function t we don't know anything about. It could be really, really large. Nevertheless, there is such a function. And without loss of generality, we can assume that t is weakly increasing also. So if t was not increasing, we could just replace t by a new t that sums up the old t for all values up to the size that we're looking at. And it's still a bound on the running time, even though far from being sharp, being a strict bound. But it's a bound and it's weakly increasing. And also we know that we at least have to scan the whole input. So t will always be larger than the argument. Now we want to show that this language can still be decided in FPT, which means that there must be some way to hide this potentially humongous t inside the f of k part. So the t can be large, so we don't know anything about it, so we have to hide it in the f of k part of the FPT runtime bound. And what follows is essentially just a clever definition of a function that makes this work. Let's write down the function over here. We define a function h which is the largest m, so that g of m is still less than n, the parameter that we're given. We can only do that sensibly for large enough n, and for the others we just define it as 1. Now g is the function that we were given in the theorem that is the lower bound on the parameter of the instance. Now we have to make a few observations about this function h. Since g is weakly increasing, and unbounded, we will for sure at some point cross this line, this height n, which means that h is well defined. So it's best to imagine the following properties as follows. Let's draw the graph for the function g. We know that it must look like this. It can never decrease. It's weakly increasing, but it can stay constant for a certain time. And it's unbounded, which means no matter where you put the bar, at some point you will cross it. So, and if this is at height n, so that was g of, let's just call it g. I mean, here we should give that a name. Never mind, say m, and this is g of m. For any such n where you put the line, at some point you cross it, and the point where you cross it, that's the h of n. Okay, so it's well defined, that's good. But there's more. By the same reasoning, we also know that h itself is weakly increasing again. So all the functions that we're dealing with are weakly increasing. Why is that? Well, intuitively in the picture it's clear if I pull up this line a bit more, then the crossing point can only move to the right because g is increasing. One more property is that we can actually compute this function. So we know that g is computable, and that means also h is computable. Since we don't need a specific running time for this computability, we can just simulate this max, and we know that there's only a finite range for any n that we have to search for this max, and we can just keep increasing m until we first violate this. So this is easy. And the last property is that if we insert into h g again, h of g of n, then this must be at least n. Why so? If you insert that here, then you're just asking g of m should be less than g of n. Well, at least for m equals n, there's an equality here. So we certainly can't have a smaller result of this maximization than n. And this is what the claim says. So for any n greater or equal 1, so we are always assuming in this proof that all the numbers are natural numbers. So with these 4 properties, we're almost done. We just compute. So recall the time to decide whether x is in L. It's bounded by t of the length of x. Now since t is weakly increasing, we can make the argument larger, and the whole thing will become larger. So we use equation 4 here, or property 4, with setting n to the length of x. So we insert this, h of g of length of x. First the length, g, h, t. It's a bit messy with all the parentheses, but apart from that, it's a simple argument. Now, g of the length of x, that's exactly what we had here. So this is smaller than kappa of x, than the parameter. And since h and g are increasing, this means it's t of h of k, where we set k to the parameter of the instance. Now, and this is nothing more than some function of k, right? It can be a large function since t is essentially any computable function, but it's only a function in k. So we've essentially shown the time to decide x depends only on the parameter and not at all on the length of x. So that means that just the assumed decider for L is FPT with respect to this parametrization. So this means if you pick an inappropriate parameterization, then everything is in FPT and we don't make any interesting statements. And for example, what you should definitely avoid is having a parameter that can never decrease. All interesting parameters must have the property that if the size of the encoding of x grows, then there must also be the possibility that the parameter goes down. Unless you have this, anything is in FPT. Okay. Now, I've said that the equivalent of the class P is our class FPT. We've seen that we have to be a bit careful to not choose a stupid parameter. But there's a certain number of problems, parameterized problems, where we don't seem to find an FPT algorithm. As before, we had problems where we couldn't find a polytime algorithm. So for some problems, seem to be not in FPT. But how to prove that? Well, that's asked for a lot because we were also not able to prove that some interesting problems are not in P. So probably we won't succeed with FPT so easily, but we can use the same kind of machinery. Reductions and relative hardness. And then we will find, as before, statements like unless P equals NP, where P and NP have to be replaced by equivalent or analogous assumptions from the FPT world. Unless this unlikely assumption holds, this problem is not fixed parameter tractable. So let's first look at reductions. We call polytime reductions. That was just one language is polytime reducible to another. If I could transform an instance x in L1 so that it's in the language whenever the transformed one was in L2, and A should be a polytime algorithm. Let's write it sloppily like this. A is a mapping between languages, so it's not a decision problem, but it's this is just a shortcut for saying A has polytime. Now we'd like to generalize this to parameterized problems. So given two parameterized problems, we again consider a function A that maps the instances, but now we have to take care of the parameters. At this point I might add, it's very convenient now that we have separated in the definition of parameterized problems the language and the parameterization. If we were only allowing languages of pairs of instances and parameters, this definition would be messier. So I definitely prefer this one to the more traditional one. This mapping A from words from the one language to the other has to have the following three properties. First of all, whenever the one we're given is in the original language, the transformed should be in the language. That's exactly the same as here, and certainly something we want for a reduction. Then A has to be computable in a certain bound. Now requiring polytime here would not be fair in a sense, or would not give the results that we like, because if the parameter of the input is large, then we shouldn't request polytime here. Instead we say A is an FPT algorithm, where the parameter is the input parameter of the problem we're making the reduction from. This is also a natural requirement and just naturally corresponds to this requirement from the traditional world. Now we need a third one that guarantees us that the parameter of the transformed instance doesn't explode too much or doesn't grow without any bound. Specifically, the parameter of the transformed instance is at most a function of the parameter of the old problem, but does not depend on the length of the old instance. Right, that's the important part. Now G, again, it's the same letter as before, but G is a very different thing. Before it was this growing function and so on. Here it's just any computable function. So this bound is not very strict. This could be extremely large, but it may not depend on the length. If this is if we have such a reduction, we write this problem reduces to that in the FPT world, written like this. The problem now from the application of the theory is that many of the reductions that we've already developed for the classical P versus NP theory does not have this third property. So it's easy to see that the first two are given for a polytime reduction, but the third one not necessarily is. And as an example, just to give you a simple one, let's consider vertex cover an independent set. So we've already discussed vertex cover. Now independent set, just to quickly remind you, is given a graph and a number. Can we pick k such vertices from the graph so that there's no edges between these vertices at all? Now what you might have seen in an introductory course is that independent set can be reduced to vertex cover as follows. You keep the graph and you kind of invert the threshold. So given an instance for independent set, say a graph like this, let's add a few edges, but not too many. So then I can pick these three edges, these three nodes. They don't have any edges in between. So these are an independent set. But that means all other nodes have to be a vertex cover, because all edges in the graph are covered by these, because if there was some edge that was not covered by the blue nodes, it would be between two red nodes, and that was by definition not the case in an independent set. Now here the new parameter depends definitely on the input size, namely the size of the graph, and not only on the parameter of the input. So the old graph could have been large, even though k was relatively small. But that means for the transform problem, the parameter could grow very large, and is certainly not bounded by such a function only of k. Right? So this is, from this we cannot deduce anything about the relation of these two problems. So the parameterized problems, P independent set and P vertex cover. From what we've seen here, it's unclear whether this holds or not. So we cannot deduce anything about that because this reduction is not parameter preserving. For many other reductions, the parameter can be bounded, the resulting one, and then we can just take the same reduction that we had before. For other problems, we might find a different reduction so that the parameter is kept. And in that sense, we have to work a bit more, but it's not much different to find reductions than in the classical P versus NP world. That's great. We know reductions, but what's the equivalent of the class NP? Reductions were only half of the of the problem, we need some class so that we can define hardness and completeness against this class. And this was the class NP in the classical theory. We need an equivalent for that in the parametrized world. Now what I will show you now is a sensible definition that looks very promising, but in the end will not work out. It will not give us a suitable candidate for a class that can play the role of NP. It will have certain properties, but in the end, not the one that we want. So recall how we defined the classes P and NP. We've shown in the first lecture that NP can be given as the class of verified problems, problems that have a polytime verifier, so that given a certificate we can check whether the problem is a yes or no instance in polytime. But it's not so clear how we should squeeze in the parameter in this definition. The other definition for NP, the original definition for NP, was there's a non-deterministic algorithm that decides the problem in polytime. And this definition is easily generalized, and that's the class para-NP. So para-NP is the set of all problems for which there is a non-deterministic FPT algorithm, by which I simply mean say a non-deterministic Turing machine whose running time has an FPT bound. So the running time is at most f of the parameter times the polynomial of the input size, like we've seen before. This class does have some nice properties that we're not going to prove. But you can show that this class is closed under reductions, under the FPT reductions we've just defined. So whenever one problem is in para-NP and a second problem can be reduced to another problem, then this also has to be in para-NP. And this means that we can sensibly talk of para-NP hard problems and para-NP complete problems. Finally, also the big question P equals NP is exactly equivalent to the question, is FPT the same as para-NP? So in that sense, we found a nice equivalent of NP. And also a third property of FPT can be transformed to the non-deterministic world. That's the idea of kernelization that we will discuss in a few sessions. Even though you don't yet know what it is, I'll just wanted to add the point that this also generalizes nicely. So we could use para-NP and para-NP completeness. The definition for para-NP hard is as you would expect. So a problem is hard if every other problem from the class reduces to it. But this class has the following flaw: it's too strict. So here's the theorem, and we will only prove part of it. So it's essentially an if and only if and a characterization for para-NP completeness. I've only picked out the one implication that gives the interesting message, and therefore maybe we don't need this technical requirement here. Let's prove the one direction. So we have a parameterized problem that is para-NP complete, and then it's true that also the following problem is already NP hard, namely the problem L less or equal D, which is just the instances where the parameter is at most D. I should say this is actually an existential statement. For any problem L, for any parameterized problem L, there is some constant D that doesn't depend on the input but on the problem, so that this holds. Okay. Before we discuss the meaning of this, let's quickly prove this. So we assume that we are given this para-NP complete parameterized problem L kappa. Now assume we pick an arbitrary language L prime that is NP complete. Take your favorite set or whatever. Now we can make this a parameterized problem by adding a dummy parameter, one that doesn't really do anything sensible, by just setting the parameter to 1, ignoring whatever comes. So I claim that this parameterized problem is in para-NP. Well, we have to show for this, we just have to show there's a non-deterministic FPT algorithm. Well, but we know there's even a non-deterministic polytime algorithm. And simply ignoring the f of k part already shows that there's also a non-deterministic FPT algorithm for L prime. So for sure this holds, right? So we have a parameterized problem that's in para-NP. Now our L kappa is para-NP complete, so there must be a reduction from this strange parameterized problem to our problem L kappa. And this is where the trouble starts, because the parameter of this problem is just bounded by this constant, right? Now let's do it in detail. What does it mean that we have this reduction? There's an algorithm A, so that whenever x is in L prime, the transformed instance is a yes instance for L, is in L. A is an FPT algorithm. Well, with respect to which parameter? The parameter of the input, which is kappa 1. So its running time is at most f of k times some n to the c, some polynomial of n. But this k is kappa 1 of x, which is just 1. So essentially what this says is that A runs in polytime, right? And finally, what's the parameter of the resulting problem? By the definition of FPT reductions, there is a function g, so that this only depends on the parameter of the input. And this again is just 1 by definition. So it also means that the parameter of the new instance that we created from this must be bounded by some constant. And this is how we will set our d from the theorem. So we found, plugging this together, we found a polytime reduction. Namely just the algorithm A. From the language L prime to the language L lesser equal D, which is just all instances of L that have a parameter at most d. And that just means, so recall that L prime was an NP-complete problem. So we reduced an NP-complete problem to this new problem. That means this is NP-complete. And that's what we claimed here. This is NP-hard. Okay, NP-complete, I haven't talked about being in NP, so we should keep that correct. Now, what does it mean? The interesting statement is the converse, is the contraposition of this statement. If we have a parametrized problem so that there is, that's not NP-hard, if you fix the parameter by a certain constant, then it's not going to be para-NP complete. So the implication is that only very few problems can be para-NP complete. Well, we have some examples, which is the graph coloring problem that we've discussed before. Namely, okay, we haven't proven here the converse, but I said it's true. So for the graph coloring problem, we know that if the parameter, the number of colors is 3, then it's already NP-hard. And then by the converse direction I haven't shown, the problem is para-NP complete. But for much more, for the larger class of interesting problems, I've give just a few examples. P-clique, P-independent set, and P-dominating set. We know by the brute force method that if we fix the parameter by a constant, there's an FPT algorithm, or there's a polytime algorithm, sorry. For these problems, they cannot be para-NP complete. Since fixing k less or equal d for some given constant d makes the problems polytime solvable. So again, just take the simple brute force method. Take the clique problem. If you fix k, then it's an n to the k algorithm, essentially n to the k times some polynomial in n to solve the clique problem. But if k is fixed by some constant, then this is just a polynomial. So these problems can all not be para-NP complete. But at the same time, we have reason to believe that they are not in FPT either. So I mean, again, we would like to prove this, We don't know, but we suspect that they're not in FPT, and we would like to prove this. But the whole idea of para-NP completeness is completely useless for making progress on this, because they for sure are not para-NP complete. So not even in this, under the assumption P not equals NP sense, can we say that they're not in FPT. Para-NP completeness does not help at all here. Let's say the para-NP theory does not help in settling complexity, the true complexity in the parametrized sense. Of these problems. And indeed, this is the much more wealthy and interesting class. There's certainly a few more of this kind, but these are actually the parameters that are not really helpful. If fixing the parameter by a given constant that only depends on the problem already makes the problem NP hard, then this is actually not a good parameter, because we can't expect this parameter to be even smaller than this magic NP threshold. So we will have to see next time how we can improve on the definition of para-NP, how we can find a different hardness notion that helps us in making progress on these complexity issues. But the main motivation of this para-NP digression was to show you, or to motivate, why the definition to follow is not quite as natural and straightforward as in the NP case, because the straightforward method just doesn't help in this case.